Okay. Thank you, Hossein, for organizing this nice one-day event. So, I'm going to gather a series of the papers that I had and connect them. And I'm going to divide my talk today to two parts. One part is less technical, and the other part is a little more technical, but I'm going to avoid any details and technical proofs. So let's go. We have three systems of differential equations here, nonlinear systems. So the question is that what is the common properties among these three systems? What we can see first is the equations, the form that we are writing the equations. And if we look to all these three systems, we can find that we have here T1 squared, T1 squared, and T1 squared in all of them. And then in the rest of the equations of any system, we have T1 multiplying by the same variable that we have here. You can see that for T3 as well. And the rest is free of T1. The rest of the terms are free of the T1. So this is why what we can see in the equations included in the systems. But what other properties we can find that, let's say, geometrical or algebraical properties, or with respect to solutions? Actually, this first system here is the Ramanujan system. And we know that the solutions are E2, E4, and E6. I think Jose wrote the Eisenstein series. I'm not going to write again. So, so we have the solutions of the system are modular form, or better, quasi-modular form, because E2 is quasi-modular and E4 and E6 are modular forms. And Jose also told this fact that we know that the space of modular forms and quasi-modular forms is generated by E2, E4, and E6. In fact, the space of modular forms, quasi-modular forms for SL to Z is a graded algebra. The direct sum of a space of quasi-modular forms of weight K for SL to Z. K is 0 to infinity. So here we have a graded algebra, and it is generated by Eisenstein series. And the same things is happening for here. Okay, I told that T1 is E2, then T2 is E4, and T3 is E6. So, and the space of modular forms is generated by just E4 and E6. And if we look to the other two systems as well, we see that the solution of this system is again can be written in terms of quasi-modular forms. The T1 again is a quasi-modular form, and T2 and T3 are modular forms. And here, these three solutions generate the space of modular forms over gamma naught 2, and T2 and T3, these two solutions, generate the space of modular forms for gamma naught 2. And we find the similar properties in the case of the third system, but here the space of modular form and quasi-modular form generated for gamma naught 3. Okay? And here, this eta is dedicating eta functions. Again, is a modular forms. Eta of q is q power 1 over 24, 1 minus k power n from 1 to infinity. I think I'm right. So, but the reason that here I wrote in this form because we have a relation between T3 and T2 and T4. So we need to divide for this idea, or consider the quotient by this idea. So another property in common is that all of them have solution as modular or rather quasi-modular forms. And one more thing that I call your attention here is about the weights. What is the weight of E2 is 2, E4 is 4, and E6 is 6. And the numbers that you find here, 4 and 6, are the weight of these two. The same thing happens for the rest of the system. For example, here, T2 has weight 2 again, T3 has weight 4, and T4 has weight 6. So you can see the numbers here. And T1 always has a, T1 in all of them is a quasi-modular form of weight 2. And the coefficient that appear here is 1 in all of them. So this is another point in common. So let's go to the next.
How many of these are known? How many of these are known? If I give you gamma naught n?
Sorry?
How many of these are known? If I give you some gamma naught n, can you write down a system like this? The generators of quasi-modular forms for gamma naught n.
I'm not, I can't.
You have quasi-modular forms for n equals 1, 2, 3.
Yeah.
The system. How many n can you do?
We can do that for all of n. Yeah. But the reason that this one is Ramanujan, it's coming from a family of elliptic curves that Hossein worked on it first, and then R2 and R1 are coming from the Dwork family. I will explain in the second part where are coming these two systems, okay? And I will give some equivalent properties that we will see that we can find such a system for all gamma naught n. So the other property that we have here is the, okay, we have a graded algebra, so we can endow this graded algebra with a SL2C modulo structure. How we can explain that one? Actually, here D is a derivation, yeah? Because we saw that the space is generated. The space is generated by these three solutions. So the system exactly is giving the derivation on the space to us. That derivation here is exactly the logarithmic derivation, yeah, for the modular forms. And then I'm considering other two derivations, W and delta. W here, if we look to the space as a graded space, it is somehow the weight derivation. Let's say, if I apply W to any of our, for example, I apply W to T1, I will have 2, which is the weight of E2. If I apply W to T3, I will gain 6, which is the weight of the E6. So W is the weight derivation or the weight operator. And then delta is a constant operator or constant derivation, just deriving with respect to T1.
It's actually the 2 times T1, right? And 6 times T3.
Yeah, exactly. Exactly. Or, yeah. So, it happens for the other 2 systems as well. And for all of them, we have the weight and the constant operator or constant derivation with respect to T1. And another things that we can see, what is the kernel of delta? For example, in the first one, the kernel of delta is exactly the space of modular forms. Let's say, because it's derivating with respect just to T1. So the kernel is the space of modular forms. And it happened for all of them. And we can see that. Just let me to write the Lie bracket for the, if we have 2 derivation, let's say R equals to summation of Rj d dtj, and let's say j from 1 to d, and h equals to hj d dtj. Then the Lie bracket of R and H, we can compute them in this way. It will be equals to R of Hj minus H of Rj d dtj, j from 1 to d. If we compute for d, w, and delta, these brackets, we find this relation here. D and delta will give W, WD gives 2D, and W delta gives minus 2D, 2 delta. And these relations, it says that we know that the space of SL2C, the Lie algebra SL2C is generated by, let's say, F equals to 0, 1, 0, 0, G, H equals to 1. Let me just check. Yeah. So this is A, this is F, 0, 0, 1, 0, and H equals to 1, 0, 0, minus 1. And the bracket, Lie bracket of the matrix here, A and F is H and E is 2E, and H and F is minus 2F. So we can see that here. We have exactly the same brackets here, so we can just sending D to E, W to F, and delta to H, and we will have this relation. So we have a SL2C modular structure over all of these graded spaces. So we discovered these properties, and we're gonna extend this kind of the structure, this kind of system, define a class of the systems. Here, I think I wrote, yeah. We are working with, in the case of the modular space, we have just positive weights, but now we are going to consider a graded space or graded algebra that the weights can be rational as well. Here is a natural number. And we suppose that we have a derivation. If you look to the derivations in the previous cases, let me just show in the case. In all of them, D increases the weight by 2. For example, if you look at here, D, here T2 has weight 2, T1 also has weight 2, so the weight here is 4. Here also the weight is 4, because T3 has weight 4. And this one also has weight 4. So the weight of T1, here the weight is 6. Here is 6, here is 4, here also is 4. So T1 has weight 2, but the derivation has weight 4. T2 has weight 2, the derivation has weight 4. So all these derivations increases the weight by 2. In the other word, the derivation is of degree 2. So the derivation that I'm considering here for M, it increases the weight by 2. I mean, it sends MK to MK plus 2, the elements of MK. The elements of degree K sends to elements of degree K plus 2. And then we consider this system. We are supposing that T1 and Td somehow are generated of the graded space. The graded space is of finite, is finitely generated. So we let the derivation of T1 be T1 squared plus a polynomial just in this part of the polynomial just appearing T2, T3, and Td. Then for the rest of them, we always multiplying T1 plus any Tj by the weight of Tj. Let's say here W2, W3, and Wd, they are the degree of T2, T3, and Td. And the rest, we have a polynomial of degree Wj plus 2. So we are calling this kind of the systems Rankin-Cohen type, Ramanujan systems of Rankin-Cohen type, or just RRC system. In a few minutes, you will see why Rankin-Cohen appears here. But what are the properties of the system? The same as before. D is always of degree 2, is a derivation of degree 2. And this system, this derivation or this system, together with the weight operation and this constant operation, is isomorphic to Lie algebra SL to C. But the question is here is the converse of this one. If we have a graded algebra with a derivation such that the derivation with the weight operation and with another derivation gives a copy of SL2C, can we find a system of the generators that it can be written in this way? And the response is yes, we can do that. And it is a theorem that I proved it with Bogo. Let's say we have a graded algebra with a derivation of degree 2. We have delta. Delta is a derivation such that our graded algebra can be written as a kernel of delta. Let's say polynomials in T1 with coefficient in the kernel of delta. If you look here, I wrote, yeah, actually, M tilde here, the space of quasi-modular forms, is generated by M T2, yeah? Because our M was C of T2 and T3. Sorry, T1. Here are you roll? Yeah, it's T1. Because this one is T1, T2, and T3, okay? So we need that the derivation delta satisfies this condition, and we also have the W is the weight operation. Then we can extend T1 to a set of the generators such that we can have such a system for all the generators. Let's say we can have an RRC system. And here I'm giving another example. This example is coming from the mirror quintic. In the case of mirror quintic, we find this derivation. But if we look at this derivation, if we look them in a graded space, graded algebra, they are derivation. But we can consider them also as a vector field.
So is R3?
Hmm?
R3 is your D?
Yeah. R3 is D, exactly. And we have here the weight operation. We have here the delta. But if you look here, delta is not the same as before. And W here is what? For example, here, T4 does not appear. It says that the weight of T4 is 0. But here, if we look to the derivation of T4, we have T2 is appearing here, T4. So this derivation is not, or let's say the system associated to this derivation is not the same as RRC system that we knew. But it is isomorphic to SL2C. This 3 derivation gives a copy of SL2C. So the idea is that we can write it as a RRC system. And actually we can, just if we consider, instead of T2, we consider minus T2. Instead of T7 plus T4, we call this one T7 tilde. And since I want the polynomials, if you look here, we have these divisions. So since I want polynomials, I'm considering this division as a new variable. But it has now the weight, negative weight. Let's say here, T1 has weight 1. T2 is playing the role of quasi-modular form here. And T3 has weight 3, T5 has weight 5, and the rest. So by these changes, we can write the system as a RRC system that as an RRC system that I told you. And another important thing here is that now we have elements of negative weight, and also we have element like T4, which is not constant but has weight 0. So, but what Rankin-Cohen bracket? I'm just going to give a very rapid definition, and I'm not going to enter to details. For example, in the case of the modular form or quasi-modular forms, if we define this relation, look, for example, in the case of E4, the derivation of E4 is, if we look here, the derivation of E4 is E to E4 minus 1/3 is 6. Yeah? So the derivation of E4 is not anymore a modular form. E4 is a modular form, the derivation is not a modular form. Because it appears E2 here, E2 is a quasi-modular form, and we don't have any more a modular form. But in this definition that I considered here, actually Rankin and Cohen, in this definition, if you see, we have a F is a quasi-modular form of weight mk, of weight k, G is a quasi-modular form of weight L, and if we consider these strange relations between derivations of F and G, then in the case that F and G are modular forms, this bracket, the nth bracket of F and G, remains again a modular form. Let's say the space of the modular forms is closed under these brackets. So who proved this fact is Cohen, and Rankin gave some relations, and Cohen generalized his relations and proved this fact with respect to the modular forms. So Rankin-Cohen algebra is exactly is an algebra, is a graded algebra with a bracket that satisfies all algebraic conditions satisfied by the bracket, Rankin-Cohen bracket of the modular forms. So if we have a derivation of weight 2, now let's talk about a general graded space like M that I defined here. And then with the derivation of degree 2, and we define with respect to this derivation, and then we can define see, we have a bracket like this that satisfies all algebraic conditions which is satisfied by the Rankin-Cohen brackets. Then we call this algebra as a Rankin-Cohen algebra. And the fact that I just wrote here, I gave just definitions in the case that we have this derivation on the whole space we consider is this algebra as a standard Rankin-Cohen algebra, and on a subalgebra, when we have, for example, in the case of the modular space, which is closed under the bracket, we call this one as a canonical Rankin-Cohen algebras. So, what we proved until now. So, having RRC system is equivalent to have a SL2C module structure over over our graded algebra. Another equivalent condition is exactly coming from the Rankin-Cohen structure. And the theorem is this one. If we have a RRC system, then the algebra generate, obviously we have the system, we have a derivation of degree 2, so the whole space is a standard Rankin-Cohen algebra. And if we consider the space generated by T2 until TD, just we are not considering the T1 that is playing the role of the quasi-modular form, then we have the canonical Rankin-Cohen algebra structure here. And conversely, every finitely generated canonical Rankin-Cohen algebra arises in this way. In the other word, if we have a Rankin-Cohen without a derivative, if we have a Rankin-Cohen algebra, canonical Rankin-Cohen algebra, we can find such a derivation D, a derivation W, and delta, and we can recover the RRC system. So another equivalent relation is having the canonical Rankin-Cohen structures. So why all these conditions are important? We will see in the final, on the final of the talk, and we will see why these conditions and how we relate them. So here I finished the first part, and now second part. What is R1, what is R2, and what is R3, and how we find them. So this family, Hossein talked about this one, also Mohammed talked about this one, but in the case of 3, n equals to 3. But for any n, we can consider this family, which is known as Dwork family. Inside Pn plus 1. And then we have this group, exactly the same process of constructing the mirror quintic. We have this group acting canonically just by multiplying the components. Then we are considering the quotient is singular, we desingularize the quotient, and we will have a Calabi-Yau variety. We are calling it the mirror variety. By the way, this one is a part of the paper that I had with Hossein. And what we know about mirror variety, we know that the dimension of a mean Hodge structure, the middle Hodge structure, let's say H and dr is n plus 1. All Hodge numbers are 1. And we define, Hossein today talked about the small modular space when he was considering just X with alpha, which was a regular n form. But now we are extending the n forms to a basis of the Durham cohomology. But these alphas, they have to satisfy these two properties. The first one, alpha i's should be alpha I belongs to, here f i's is the Hodge filtration, yeah? I don't know if I need to write it, but we have here F0, F1, and Fn plus 1, which is 0, yeah. So any alpha 1 is here. Sorry, alpha it belongs to any Fn plus 1 minus I. So alpha 1 is here, yeah. Then alpha 2 is here, but it's not here. Sorry, it's here, but it's not in the next one. Alpha 1 is not here. So, and also the intersection form matrix here, it also should be a this constant matrix. By intersection form matrix, intersection form here we mean this integral. So our basis, it needs to satisfy these two conditions, and phi n is this constant matrix if n is odd, and it is exactly this one if n is even, because it is minus 1 power n symmetric. So considering this modular space, here comes the theorem that, we are constructing the universal family. Then Hossein talked about this one also today. The modular space, the whole modular space will be this spec of this expression here. In the case that Hossein talked today, we don't have T3 until TD, but in this case, because it is extended, so we have all of them. And we are also considering the Gauss-Manning connection on the relative algebraic Durham cohomology bundle. So we have the Gauss-Manning connection here, and here comes the theorem. There exists a unique modular form on the space of a unique vector field on T, and unique functions, regular functions, y1, y2 until yn minus 2, such that we have this equation satisfied by R and by yi's. So, and also we find the exact dimension of T. So the important part is here. And here we find the vector field over our modular space. So this vector field that is giving the derivations that we were considering. In the case n equals to 1, we find the R1 that we had. In the case of n equals to 2, we find R2. And in the case of n equals to 3, we find the case of the mirror quintic. So here and the interesting part is that in the case of mirror quintic, Hossein found that this function y1 is exactly the Yukawa coupling of the Candelas, De La Osa, and the rest of the authors. Why? Because he's finding the solution of the R. Let's say, I think I put here the, in the case of 4, we can't find, if we consider the vector field as a system that we saw. For example, in the case of n equals to 4, our vector field, we can consider it as this system. And you can see system is exactly the same as RRC system. Just up to this negative, instead of T2, you consider T2 minus T2, and T2 is playing the role of T1 that we had. So T2 is playing the role of the quasi-modular form, and the rest are playing the role of modular forms. So again, Hossein has an algorithm. We can find a solution as a power series for this system. And when we find the solutions up to the first one, all of them are integer numbers. But they are not modular because they are not modular formed, let's say, because the coefficients are increasing very rapidly. But they have properties in common with modular forms. What were the properties? In the case of the modular forms, we have exactly the canonical Rankin-Cohen algebra structure. We have this modular structure on the space of the modular forms. So the way that we are finding the modular form, the vector field R, we just need to observe somehow that we have this canonical Rankin-Cohen structure or this form of the system. We just solve the system just for n equals to 1, 2, 3, 4. But we can prove for all of them. To prove this one, we just need to observe that R together with the weight operator and another operator give a copy of SL2C. And this is what we can see in the next. By the way, in the case of n equals to 4, if we compute the coefficients of y1 squared, then we find exactly the 4-point function given by Green, Morrison, Placer in their paper. So we have much more other evidences that we are in the correct way. And just to say how we can find this SL2C modular structure given by R, again, the same way that we found R, now we are defining another Lie algebra here. Let's say a Lie algebra of matrices. And for any matrix in this Lie algebra, again, we find a unique vector field that satisfies an equation similar to the one for the modular vector field R that we found. So, to any element of Lie algebra, we associate a unique vector field. And we can say that somehow this Lie algebra is a subspace of the space of the vector fields of the T, our modular space. But in the case of this choice of the matrices G11, G22, and G12, we can prove that if we define W, the vector field associated to G11, delta to G12, and the rest for the other cases. This is in the case n equals to 1, n equals to 2, and this one is for n greater than or equals to 3. If we define W and delta in this way, they give a copy of SL2C. So R together with this W and delta is giving a copy of SL2C. See, if it is giving a copy of SL2C, always we can find an RRC system associated to the space of the solutions of this vector field, or a canonical Rankin-Cohen structure to the space of the solution of this system. So, looking in all these cases, in the case of the modular forms and the way that we are considering the chart and the rest, here T2 is playing the role of E2, the quasi-modular form, and the rest, T1, T3, until TD, they are playing the role of the modular form. So for us here, Hossein gave a definition of the Calabi-Yau modular forms today, but the definition now I'm giving in the case of the Dwork family is a little different. So for me, the space of quasi-modular forms is the space generated by all the solutions divided by discriminant that we have here, and the space of Calabi-Yau modular form is just put T2 out of this space. And the space generated by the rest is giving the space of the Calabi-Yau modular forms. So,
yeah, but maybe this is not a good definition. Calabi-Yau modular form has the ability to make two elements.
in the case of the Dwork form,
These are still all class 1 modular forms.
Yes, but with my the property that I saw here, for me, the space of the modular form is this one. But okay, you are telling maybe there are more quasi-modular forms among them, but by the properties that I verified and by the analogy that I constructed, for me, this one is the space of the Calabi-Yau modular form, and this one is the space of Calabi-Yau quasi-modular forms. And actually, we can see that M tilde is M of T2. And I'm going to finish with the mirror map. So in the case of mirror map, we found another example, other functions that found by physicists that we can write in terms of these Calabi-Yau quasi-modular forms or Calabi-Yau modular forms. And another example is the case of the mirror map. For the Dwork family, the mirror map, we can find that the mirror map is given exactly as this quotient. T1 has weight 1, Tn plus 2 has weight n plus 2, so the quotient has weight 0. So we have the z, and z is exactly our parameter. So after computing this one, comparing but the solutions that we find in all the cases, mirror map here, exactly what we find is this function, which is the one found by Leon and Yau. The same case, the same happens in the case n equals to 2 and n equals to 3. They are exactly the same mirror maps that Leon and Yau are finding. And in the case of n equals to 4, also is the one computed by Clem and Placer and Pandaripande in 2008. So we can write the mirror maps in terms of Calabi-Yau modular forms. So somehow, I'm trying to find still more evidences. And this structure, this Rankin-Cohen structure or Rankin-Cohen algebras, now I'm working on another problem, that somehow I'm trying to associate to any RRC system, let's say a Calabi-Yau modular forms, which will play the role of new form of weight 2, exactly the new form that is coming from the modularity theorem, somehow. Okay, it's in progress. I don't know if I can solve it or not, but I'm trying to associate to any RRC system one Calabi-Yau form of weight 2 and then using that one, maybe finding a function, or I don't know, and continuing the studies, but still they are open for me and I'm working. Okay? Yeah, I could finish 10 minutes before.